factual düzeltme yapayım yanlış anlaşılmasın diye. Şirketten değil bu şeyden Alexander von Humboldt Foundation var. Onun bir fellowship'ini aldım. Herhalde onu sen söylüyordun.
Yanlış anlaşılabilirim. Evet hocam.
Şeyde postdocumu da aslında Harvard Medical School'da yaptım. Orada Brigham Women's Hospital, Harvard Medical School'la affiliated bir hospital'da yaptım ama bizim laboratuvarın MIT'de de affiliation'ı vardı. Tekrardan teşekkür ediyorum. Yani bu tarz bir organizasyon yaptığın için özellikle de sana çünkü bir sürü insanı bir araya getiriyorsun. Ben şöyle yavaştan da ekranı paylaşıyor muydum şu anda? Ha, zaten paylaşıyordum herhalde.
Evet,
değil mi?
Evet.
Tamam.
Evet.
Şuradan bir de şey yapayım. Presenter view'a geçeyim. Başlayabilirsin diyorsan başlayabilirim artık.
Tabii hocam ben size bırakıyorum. Kameramı da kapatayım kasmasın. Siz rahat rahat konuşun. Dinliyoruz sizi.
Tamam. Herkese teşekkür ediyorum katıldığı için. Bu arada ben yani 13 senedir Amerika'daydım. Ve yani bir 11 aydır falan buradayım. Hala bilimsel dilimi Türkçe konusunda hakim değilim. Onun için böyle karşınızda tarzanca konuşmamak için İngilizce bir sunum yapacağım. O açıdan biraz eksik hissediyorum kendimi Türkçe sunamadığım için. Onun için kusura bakmayın. İngilizce de devam edeceğim bu noktadan itibaren. So today I'm going to talk about magnetophoresis-based technologies for point-of-care diagnosis and complex material fabrication. So I have two teams in my laboratory. The first subject is basically focuses on three applications that we have explored over the years. These are sickle cell diagnosis, CTC, circulating tumor cell detection, and neutrophil count. And the second area is bottom-up biomaterial fabrication. So this area covers a broad range of topics, such as regenerative medicine, pharmaceutical engineering. So if you first focus on the first application, so we should first, before diving into the technology, we shall define the disease, the sickle cell disease. So the sickle cell disease describes a group of inherited red blood cell disorders. So people with the sickle cell disease have abnormal hemoglobin called hemoglobin S or sickle hemoglobin in their red blood. So hemoglobin is a protein in red blood cells that carries oxygen throughout the body. And inherited means that the disease is passed by the genes from parents to their children. People who have sickle cell disease inherit two abnormal hemoglobin genes, one from each parent. And in all forms of sickle cell disease, at least one form of the two abnormal genes causes a person's body to make hemoglobin S. So when a person has two hemoglobin S genes, hemoglobin SS, the disease is called sickle cell anemia. This is the most common and often most severe kind of the sickle cell disease. Other than SS, there are various types of sickle cell disease such as SC, S beta. So here figure A shows actually normal red blood cells. So the top view, normal red blood cell flowing freely in a blood vessel with normal hemoglobin. On the other hand, the bottom image shows abnormal sickled red blood cells and blocking blood flow in a blood vessel. And also the inset image shows a cross-section of sickle cell with abnormal hemoglobin forming abnormal stiff rods. So normal, as I said, normal red blood cells are flexible, so they can move through large and small blood vessels to deliver oxygen. And sickle cells are not flexible and can stick to vessel walls, causing a blockage that slows or stops the flow of blood. So when this happens, oxygen can't reach nearby tissues. And you can see some of the symptoms of anemia in this image. So the red sickling and poor oxygen delivery can also cause organ damage in addition to all these problems. So an important clue is red blood cells in people with sickle cell disease have been observed to become dehydrated and increase in density. So increase in density of these red blood cells. So this mechanism is believed to arise from a combination of hemoglobin S polymerization accompanied by a change in the activity of cation transport systems, and under deoxygenated conditions, so lack of oxygen conditions, the HPC molecules polymerize to form long rigid fibers, which aggregate and cause red blood cells to take on a characteristic sickle shape. So with this rationale in mind, and the fact that there's an unmet need for rapid and reliable diagnosis of sickle cell disease at high throughput in remote settings, we therefore started to work on a power and chemistry-free method to sort cells based on their volumetric mass densities. So remember, the density is changing with this disease. So here you see a very so you see the schematic of the simple sensor. So the takeaway message here is so basically, as I said, the volumetric mass density of red blood cells as an important parameter to monitor. We started to think how we can use this property to be able to sort the cells. So here you can see two permanent magnets in the subfigure A with same poles facing each other. So that is called in the literature as Untitled configuration, and it is called also magnetic levitation. So we place a suspension of particles or suspension of cells in a biological application in between these two magnets, and then which I will describe more the physics, but by placing this this sample, we are able to separate particles. So as I said, magnetic levitation has been out there for decades, actually, to move big objects like trains and decrease the friction to enable faster and more efficient transportation. But it's basically creating magnetic field which cause objects to move from high magnetic field strength to low magnetic field strength in a relatively more paramagnetic liquid. So in this case, the liquid we have here is more magnetic. So I will also describe this fluid in the coming slides. But the particles themselves are diamagnetic, so they are not magnetically responsive. So the liquid itself, the suspending liquid itself, is magnetically responsive. So we demonstrate this application on cell manipulation here by several iterations on the magnetic field strength to be able to hit that sweet zone where we can match the magnetic force with beyond force, so that cells are not floating or sinking to the bottom of the capillary that we have here, or the reservoir we have. And we have to identify, as I said, biocompatible paramagnetic media. And in this case, we use an FDA-approved MRI contrast agent, which is Gadavist. So I hope no one here had any MRI treatment, but if you or any family member had experience, so they inject this magnetic fluid into your vein, and so we use one of those MRI contrast agents in this project. So it's basically a magnetic liquid. So let me see. So once we came from this problem-oriented perspective. So we have to separate the particles in a remote, resource limited setting. So it should be power free as much as possible, and chemistry free, so that we don't use expensive biological reagents. So we come up with this permanent magnet solution. So here you see some of the demonstration. Here in sub-figure A, top left corner, you see the densities of several blood cell types. So, for instance, erythrocytes, which are red blood cell, or eosinophils, or neutrophils, white blood cells, or basophils, lymphocytes. So all of these have different volumetric density range. So their densities are different. So here, in the B part, once we place this blood suspension, cell suspension, together with this magnetic liquid, we were able to separate, for instance, lymphocytes, neutrophils, and red blood cells. And here we also stain these cells to be able to show that we are able to separate these cells. I hope my connection is good. So time to time I'm hearing some noise, but I assume my connection is strong. So all right. So in sub-figure C, we see that. So the idea here, so using this magnetic liquid, right? So then the natural thinking would be, what if we change the concentration of magnetic liquid? How would the particles react to this change in the magnetic responsiveness of the liquid? So what we did here in the sub-figure C, we changed the magnetic susceptibility of the liquids that we place into the reservoir that I showed in the previous slides, that goes between these two permanent magnets. So we have 20 millimolar up to 100 millimolar. As you see, while the particles at the beginning, maybe you can see in the sub-figure D as well, the particles are heterogeneously distributed within the reservoir at the beginning, but once they are exposed to the magnetic field, then they start to get confined, and that confinement height is changing based on the concentration of the magnetic liquid that we're using. So as you see at the 20 millimolar, the particles beyond force is so active, so the magnetic forces are so small, the particles are closer to the capillary bottom surface. But once we increase the concentration of the magnetic liquid, which means the magnetic responsiveness of the liquid is increasing, then the particles starts to levitate within that liquid. So in this case, we have the cells, or maybe in the sub-figure C, we have these plastic particles. But the main message here, the levitation height is tunable by changing the magnetic responsiveness of the liquid. So another demonstration here. So for instance, separation of the young and old red blood cells. So we know that the red blood cells in our body periodically generated by our body, and they circulate within our body over a long period of times. But as they get older, they new red blood cells are generated, are produced by our body. So what we did here, first we collected blood, and then we, by a density-based, another separation method, we separated these young and old red blood cells, and then we spike in this fluid, this magnetic liquid, and then we show that we are able to separate these cells again with our novel approach, and that's what we did. We showed here in sub-figure E, we are able to separate these new red blood cells from body and old, which are, I assume it was maybe a week older or 2 weeks older red blood cells that are collected from the same person. So just to avoid too many, details, but basically we are able to separate these different blood cells by using very simple sensor, two magnets whose strength has been optimized so that we can hit that sweet zone where we can match the beyond force that is acting on those cells with magnetic fields. Once we find that sweet zone, we are able to separate these different cells. All right. So once we created this power-free, chemistry-free sensor, our logic from the very beginning was applying this technology for point-of-care settings, right? So when we say point-of-care settings, resource-limited setting, what are we really talking about, right? So we shouldn't have any expensive equipment. We're talking about, in many cases, remote settings in some developing countries like Turkey, right? Not a developed country, but developing country. For instance, say some village in Hakkari or Urfa, whatever, and also less developed countries like many African countries where they don't have any critical hospital settings, right? So no expensive equipment, no well-trained technicians, limited electricity. So these are the settings that we are trying to adapt and create some valuable, diagnosis or monitoring for the potential patients. All right, so here, as the first sensor, we directly continued with a smartphone, right? So we created this, again, a simple attachment for the smartphone. So we had this plastic, we designed this plastic attachment, which holds two magnets in place, right? You can see in the subfigure E, two poles with same, two magnets with same poles facing each other. Again, we adapted a lens, an external lens, additional lens to be able to actually change the focal point of this smartphone and to be able to create a high resolution field of view. And you can see in the subfigure F and G at the beginning at time 0 when you place the reservoir or capillary which suspends this plastic beads or cells, and when you place this reservoir in between these two magnets at the beginning, they're heterogeneously, they're all over the capillary, right, in the subfigure P, F. And then in the subfigure G, you see that the particles are get confined. So all these particles at the top and at the bottom, they confine and they equilibrate at a certain location. So we don't see any separation here because this is a plastic bead. Basically, we purchased from a company that is selling these plastic beads as some particular density with some tolerance, right? That was what expected. So we wanted to show that we're successfully confined the same density particles a certain height, and our smartphone, our attachment, is capable of resolving the image, right? So that was the main goal. And then here we again show the theory of the sensor. Basically, at the subfigure C, you see that the darker region, the center of that darker region. I'm not sure if my mouse cursor is visible by you, but this center is where the magnetic field strength is cancelled. So there is no, at the very center of that dark region, there is no magnetic field anymore because two same poles, the black regions are the magnets, two same poles facing each other. There is this pure symmetry, right? The same magnets. And so we have high field strengths at near the magnets. So as I said in a couple of slides before, the particles all around here are escaping from high field strength to low field strength, which is the center line. And while they are escaping due to the beyond force acting on these particles, which you can consider as the corrected gravitational force, their weight. So it is balancing at certain height. So it's not capable of going this center line, but depending on their densities, at a certain point they are getting equilibrated. So if they are denser, then they are getting equilibrated at a lower location. If they are lighter, they are getting equilibrated at a closer location to the center line, right? So that makes sense. So again, so in G, you see that a time lapse. So at time equals 0, they're all over the capillary. So this is the cross section of the capillary, right? So we're we're imaging. So if you consider my finger as the capillary, so we are imaging from the perpendicular to this capillary, right? So therefore, we are seeing this cross section of the capillary. So at that cross section, at time equals 0, they're all over. But once the time elapses, the particles are confined. All right. So we also investigated some thermal effects because the cell phone is, warming up. Whether the susceptibility of this this liquid is changing or not. So we investigated those. So I'm just gonna pass some of the slides faster because I have 50 slides. So I just want to stick to the timeline. So we also developed this application. This is a smartphone application. Basically, as I said at the beginning, we're open to working with undergrads on such components. So a talented group of undergrads designed the cell phone application to be able to run on the same smartphone and analyze this image that we are getting from the cross section of that capillary, right? So if you go back to the very early discussion about the sickle cell group, right? So we said that due to this mutation and the polymerization, the sickle cells are heavier, their densities are higher. Therefore, we wanted to show that our low-cost, power-free method is capable of separating these healthy red blood cells from sickle red blood cells. Sorry. So in sub-figure A, you can see the control red blood cells, so which are the healthy red blood cells, are getting confined in a narrower area. But in the SS red blood cells, the confinement is much larger compared to the healthy group. So these are real patient samples. We collaborated with Professor Heaney's group from Harvard Medical School. So there was a small echo, but I think now it is better. So we collaborated with Professor Heaney from Boston Children's Hospital. So he's the head of the sickle cell group there. We work with, I believe it was 13 patients. So this was 4 years ago. And so we show that there's a statistically significant difference between the control group and the sickle cell group in terms of the confinement, levitation height. All right. So once we demonstrated this smartphone setup, then we started to receive some feedback from the field, and one of the feedback was about these difficulties about the standardization, because obviously there are different smartphone brands and different lenses that are embedded already in the smartphones. So the very first feedback that we received from the field, we had a collaborator in Ghana. So the feedback was about the operating system and also the the difference of the lens that's embedded in their software in their smartphones. So we therefore created a self-contained device. So basically utilizing the same sensor, which is shown here, this red encasement. So we developed this this self-contained device, which has the screen, I believe we had the Arduino here, and also an optical setup, low-cost optical part, and also a software that's embedded in the self-contained device. So it again shows the same logic here, the subfigure E, the sickle cell disease. So I'm not gonna discuss in detail. In subfigure B, we show the workflow, right? So with a finger prick blood, you got the sample, and then in the vial you have this paramagnetic liquid, and you can either use vortex or with some handshaking. So you're dipping obviously the capillary into the vial, right? And the main logic of the capillaries is due to the capillary force. It just the capillary force, the liquid fills in the capillary, right? Then you place into this setup, this location, right? And that goes between these two magnets, and then we do the analyze. So you can see also the cross section here. So we design a focusing ring where we are able to adjust the distance between this external lens and also the camera. So we because yeah, so there's obviously some tolerance values, right? So you're fabricating this holder for the magnets, but even with laser cutter, when you fabricate the holder, there's a certain tolerance, and when you place the capillary in between these magnets, there's sub millimeter differences between uses. So therefore, we wanted to have some sort of control between the lens, the external lens we have, and also the camera. So therefore, we also designed this focusing ring. So we created these buttons for some widely used purposes like time lapse measurement, single measurement, and all those kind of things, and also with some USB port to transfer the data on demand. But if there's no laptop available, it has also Bluetooth, so it can be connected to the cell phone, just for data transfer purpose, right? So the data can be transferred to the cell phone, and then from the cell phone you can put it on cloud, and wherever the central location is, you can analyze the images there as well, or you can share the data. So again, I'm gonna go faster here. So again, here we show with the same setup, we had to do this characterization again. Although the sensor has been validated, it's a new setup, it's a new self-contained setup. We had to show these characterizations again. But basically, what you're seeing here, once the susceptibility, the concentration, the magnetic responsiveness of this liquid increasing, the particles are equilibrated faster, right? Because I didn't include the theoretical equations here, not to bombard with the theory part, but we had the theory part in the papers as well. So if you have any questions, feel free to ask at the end or email me. So we here show 4 different concentrations against the levitation heights and the confinement levels, right? So so we have additional data for here. Also, we show some data about the shelf time. So because So you may have a central location, right, in sub-Saharan Africa, let's say in Ghana. So a technician can get the samples from a village, but the device may not be with him or her during the analysis. So there may be a day or a few days, distance. So we want to also show the effects of the transportation and shelf time. So here in this slide, we again show that for the control and sickle group, we are able to show that whether the person has sickle cell disease or not, right? So the subfigure A shows that our self-contained setup is able to tell if the person has sickle cell disease or not based on these confinement height and also confinement that band distance. So levitation height and also the confinement width. So we also define the sickleness scale, combining these two parameters, and we show that the control group is just from different patients, just show itself in a very small area, while the sickle group is far away from this region. So we define the sickleness scale as a new scale that's compatible with our novel setup. But the takeaway message is the setup has been validated for sickle cell diagnosis. So at this point, if you recall the very first few slides, we said that there are different types, subtypes of this disease. So in our case, we didn't have a chance for now until now, or we had a chance, but we haven't published it. Hello. So ya if you can mute, eğer mute edebilirseniz çok sevinirim. Arada bazen geliyor. Eğer herkes mute edebilirse çok sevinirim. So so there are different subtypes of this disease. So here we haven't worked on yet the diagnosis of different subtypes like ST or thalassemia, those group. And also an extension of this project is going to be personalized monitoring. So currently, if a patient, for instance, for a sickle cell patient, he has to go to hospital every 3 months or 6 months to get transfusion. So his blood is renewed with new blood. So he's getting so they get rid of this sickled cells and they're getting a transfusion. But this interval, this periodicity is defined basically with some statistics from a large number of patients. It's not personalized. So for instance, if the patient is very active in exercising or he's getting good nutrition, if he's taking care of his health in a good way, then that periodicity can be actually larger. So our setup can define, can inform the patient when he should go to the hospital, because we're with a finger prick blood, we're able to tell the patient, hey, your level of confinements and levitation heights are becoming worse and worse, and we can define a threshold, and we can inform the patient and also his doctor when he should visit the hospital, right? So there is also that perspective, and we are working on that side as well. All right, so so just to honor everyone that is working in this field. So from Harvard University, George Whiteside, which is a very famous, well-known professor, he has contributed greatly to this magnetic levitation field. So I should acknowledge him. He mostly work on the larger setups, not these cell phone or self-contained setup, the smaller setup. So that was what we accomplished with actually my previous advisor from Harvard Medical School, then Stanford University, Utkan Demirci. So he has also greatly contributed to the field. So that was based on our my postdoc work from there. So here we also show some other application, like for instance the cancer separation. So we have this breast, I believe these blue stained cells, breast cancer cells. We are able to separate from lymphocytes and neutrophils. So we also demonstrated some of the other applications, like, so when a person gets, when the body feels some threat, or there's some sort of unknown protein, or there's inflammation, right? The neutrophils are getting activated in the body. So here we show that we're able to separate from the same blood sample. We are able to separate the activated neutrophils. So you see, activated neutrophils here as red cells from the resting neutrophils. We are able to, so this is critical because we can say that the autoimmune started to get activated due to the activated neutrophils. We're able to also, so there is also this GCH treatment, which shows that the activated neutrophils actually become again resting. Another application can be, for instance, neutrophils are also capable. They're very smart cells. They're also capable of eat basically some bacteria. So, for instance, in this case, not bacteria, just for instance, salmonella. When it eats salmonella, we are able to show that. Sorry about that. So it can also separate the neutrophils from the eaten salmonella by the neutrophil. So if you look at the image here, the eaten salmonella is separated from the neutrophil. So this is called also. Well, there are several applications, but there's also, for instance, bacteria resistance studies as well. So which my actual the postdoc advisor had some recent work on that as well. So it is there are numerous applications. So I'm gonna move to the second phase of my talk. But if you have questions at this point, I will be happy to answer before moving into the second phase. It's up to you.
Gençler, sorusu olan var mı?
Benim için de fırsat oluyor. Bayağı bir arka arkaya konuştum. Bir de şeyde bu korona döneminde fazla şeyde yapamadığımız interaction'lar bayağı zayıfladığı için bu kadar uzun süre konuşma süreçleri yaşamıyoruz arka arkaya.
İyi. Eskiden 3 saat aralıksız konuşuyorduk. Şimdi yarım saat konuşunca yoruluyoruz.
Aynen. Evet. Soru varsa cevaplayabilirim.
Korona demişken virüsleri falan hiç levitate etmeyi denediniz mi? Öyle, gerçi görmek de zor olur şeyle ama onları, ama hani levitation'a bir cevabı nasıl oluyor?
Yok, virüste nano-scale'ler çok, yani bakterilerde bile çok limited. Yani field of view burada sıkıntılı. Virüslerle hiç denemedik. Ama
ya da
onda da
virüs
işte mesela
şey yapan hücreler falan, hani virüsü etkilenmiş hücreler olabilir belki.
Yani virüslerin attach olduğu beadler olabilir. O tarz şeyler var. Yani beadler de çünkü hani virüs, ya tabii o da ne kadar bağlandığına bağlı. Yani çok sayısı yeterli olursa bir ihtimal. Yani oradan question mark koyuyor. Yeterince yüzeyi cover edip bead'in density'sinde değişiklik gösterip hani bead'e yapışıyorsa surface yani aktif bir bead'e yapışıyorsa density'sini değiştiriyorsa oradaki farkı hani ölçebilme ihtimalimiz var. Fakat daha şu anda yani COVID-19'e bunu düşünmedik ama COVID-19'e işte burada daha kabul etmedim tabii ama loop mediated LAMP metodu var. Nucleic acid amplification. Onunla ilgili bazı fikirler var. Fakat levitation'ı denemedik. O biraz zor bir ihtimal.
Hocam bu kullandığımız şeyler, bead'ler bunlar yani sisteme tutunuyor muydu sickle cell'lere yoksa yani içine mi nüfus ediyordu?
Burada yani biz bu cihazı geliştirdikten sonra bead'leri sadece cihaz düzgün çalışıyor mu? Bunu anlamaya çalıştık. Çünkü biz aldığımız bead'lerin density'lerini biliyoruz. Yani,
Evet.
yani bu bead'ler plastik bead'ler. Ve bu karakterizasyonu sadece bead'leri koyduk. Şimdi başka çalışmalarımız da vardı. Mesela sadece statik setup değil. Yani capillariye sıvı yükleyip ona bakmak değil. Onun dışında mesela ufak bir pompa entegre edip çok daha büyük volümleri mesela run etme. Cep telefonunun üzerinde.
Evet.
Mesela mililitre scale'inde sıvıları mesela şey yapma. Onlarla mesela şeyleri de denedik. Farklı density'deki bead'leri koyalım. Yani bead'ler birbirlerinden ayrılıyor vesaireyi. Yani onlar karakterizasyon için şeyde hücrelerle olan şeyde biz bead koymadık. Yani orada mesela şey datamızda Sickle cell separation'da mesela orada sadece şeyler var, hücreler var. Yani normalde aslında red blood cell'ler manyetically responsive bilinirler. Ama biz burada sıvının manyetizması ona göre tenfold'un üzerinde. Dolayısıyla orada hücreler manyetically responsive kalmıyorlar. Yani sıvının kendisi çok responsive olduğu için bu diamagnetic separation diye geçiyor literature'dan. O şekilde.
Actually, I wanted to ask something. So for red blood cells, I read something that they have some kind of paramagnetic properties. Isn't that
Yeah, so that is what I
the
was
case, or they don't?
explaining.
Could you hear me?
Sorry, the signal is not strong, so I'm not. But I think I got your point. I'm not sure if it is just me, but everyone is having difficulty in hearing you.
I can say it again. No problem. I was just asking that. I was reading a review article once, and it's over there. I read that red blood cells, when they're oxygenated, they behave as paramagnetic. Is that the
So that's
case?
true. That is true.
And
so
one of
oh, sorry. So let me answer that one because I guess there's also a few second difference. So that's true. And you said that when it is oxygenated. In our case, we are not oxygenating cells. We are deoxygenating. We are treating with metabolite. And also in the control group, we are also deoxygenating. So the normal red blood cells recovering too fast. So the amount of the agent that we're using there is so small. The healthy red blood cells are recovering itself quickly, but the sickle cells are not recovering. So there's small tuning there as well. And also a second point is, as I said, the cells or the particles magnetic susceptibilities, even if there is, in some cases, becoming so small compared to the surrounding liquid. All these particles or cells becoming diamagnetic, which means that they are magnetically, in just lay language, they are magnetically not responsive. So everything else, the surrounding liquid is responsive.
The liquid itself,
yeah, the particles themselves are just trying to escape from those magnets or those edges where the magnets are located. They're just trying to escape to the center line. When they're trying to escape, due to their density, due to their own weight, they are getting equilibrated at a certain height.
Yeah. I got it. And one more thing, if you don't mind. So
Sure.
Right now, from what I understood, like you're separating the cells in the fluid itself. But is there a possibility by using this setup, is it possible to isolate the cells themselves?
Isolate the cells themselves. So we're actually mixing whole blood with. So in some characterization experiments, we use spike samples, but in the end application, we're using whole blood mixing with this gadavis, this magnetically responsive liquid.
Yep.
So, so that's important for us because we're saying at the beginning, right? No expensive equipment, potentially no electricity. So we have to use whole blood, right?
Yep, exactly.
But we're using whole blood, but the amount of sample is relatively very small. The volume is relatively small compared to this diluting within this contrast agent, this cannabis. But we're using whole blood.
I see. I got it.
All right.
Yep. Thank you.
All right. So shall I continue? Okay.
Arkadaşlar bu kariyerle alakalı falan da soru sorabilirsiniz yani illa bilimsel olacak diye bir şey yok. Türkçe'de sorabilirsiniz hocam.
Hocam ikinci kısım da var. Bir 10 dakikanızı da alacağım.
Tamam peki hocam ondan sonra o zaman.
Kariyerle ilgili kısımları evet ondan sonra isterseniz.
Tamam peki olur hocam.
So the second phase, which is going to be a little bit shorter, I assume. So as far as I recall, and they're giving me also some videos. So the second phase is about another application, which is biomaterial fabrication or tissue engineering. We have some application in that sense as well. But again, the main theme here is using magnetics to be able to manipulate cells or cell encapsulating tissue compartments. So some of you may be very familiar with the main motivation of the tissue engineering, but just briefly, so at the moment a patient can wait months, sometimes years for an organ from a suitable donor. So this is a very overarching goal. The field is a bit far from meeting this requirement, but now there are some novel applications like creating tissues like skins, but overall, the ultimate goal is creating organs, right? Organ engineering, tissue engineering. So the conventional approach to be able to meet this demand for organs or tissues like skin or some other tissues. So cells are seated onto pre-shaped porous polymer scaffolds with a combination of molecular cues. So we first fabricate, or actually conventional tissue engineers first fabricate the scaffold, right? A rigid scaffold, and then maybe some surface modification of that scaffold, and then they seat the cells suspending liquid on top of that scaffold, and cells are just following due to some, sometimes some capillary forces, diffusion, and also some mechanical cues and chemical cues, and cells follow those cues, and they try to reach the entire 3D structure. But there are obvious limitations, right? So, the cell density may not be homogeneous. So the spot of deposition can have more cell density while the rest may have less density. So there are those kind of limitations as I actually listed here. So like achieving complex three-dimensional architectures, and also, as I said, control over cellular proximity, density, and microscale resolution. So what bottom-up tissue engineering does, so the conventional approach is called top-down tissue engineering. So you first create the big scaffold and then try to reach the inner parts. But this approach, bottom-up tissue engineering, on the other hand, you create first blocks, right, like Lego, and then with some external field, you're trying to create this 3D architecture, this big complex architecture. There, the main advantages is precision, right? You can move those blocks wherever you want, wherever the end location you like. Depending on the technology, it can be low cost, and also you can alternate between cell types in X, Y, Z directions. So some of you are, I assume actually everyone is familiar with bioprinting, right? So bioprinting is one of the technologies that can be listed under bottom-up tissue engineering, because you're creating these droplets or these these extruded filaments, right? And then with the XYZ control, mechanical control in that case, and you're able to put those cell encapsulating liquids wherever you want, right? So in that sense, we created this novel technology again. So I should acknowledge Professor Metin from Max Planck Institute. So he's a well-known professor. So I was grateful for his guidance and mentoring on the project. So what we did here as a bottom-up approach, we wanted to create these small cell encapsulating blocks. So basically, we use UV photolithography. So here, let me use my cursor. So we have this liquid. This so polymer. So it can be like gelatin, methyl acrylate, or some other polymers. So we have the cells on demand, right? In many these novel technology applications, we use these basic cell types, not patient cells. So we often use fibroblasts, just to show that our technology is good. So in this application, so we had, I believe, we have the fibroblasts. So we have fibroblasts cell suspension, right? So you can create this UV mask. Again, you can design on AutoCAD. So basically, with the UV light, the light passes, and you can create. You can polymerize. So in this case, if you have gelatin, methyl acrylate, these acrylate groups enables these precursor gel solution turns into gel blocks. So almost rigid, but it's jelly-like structures, right? So at the end, once you polymerize, once you create these small gel blocks, you wash it, right? You get rid of this liquid, and at the end you have these gel blocks that is sitting on the glass slide. So once we have these gel blocks, so here we show also L shape, right? We call these from Tetris, right? So you can create anything, any shape, right? If you have star shapes, or if you have some rectangular, so you can create any shape. So here, to be able to, once we create these gel blocks, right? These building blocks. In this specific project, we developed this magnetic approach with 8 magnetic coils. As you can see here, we have the top camera to be able to see the working area. In this case, the working area is a petri dish, right? We have these gel blocks within the petri dish, and these electromagnetic coils, which creates magnetic field, and we precisely control the magnetic field strength with a joystick, and this magnetic field strength is basically creating this crawling motion for a small micro robot. So when I call micro robot, we actually have a small resin that has these super paramagnetic particles in it. So it's basically, you can consider as a small permanent magnet. As you can see here, the image. So you're able to see my cursor, mouse cursor. So this is a small, tiny permanent magnet. You can consider it that way. And with the control of these electromagnetic the electromagnetic the magnetic field with these electromagnetic coils, we are able to make this small magnet a crawling motion, like a baby crawling motion. So there's also theory part of that, that crawling motion, which has been studied widely by Professor Steele's group in many other publications. And in this case, the main challenges are about a new environment, right? This has to match the conditions of a tissue engineering application. So, for instance, in their applications, they work with tunable roughness, surface roughnesses, right? In our case, so if it has to be user friendly by tissue engineers, it makes sense to use with off the shelf these petri dishes, right? So then you have this certain surface roughness, right? So we had several, the optimization of the micro robot motion on that roughness values of the petri dishes, because it has the stickiness, and the surface roughness is also an important feature of this crawling motion in this application. All right, so I'm coming to some more attractive parts for you. So here you're seeing a black magnets. That small tiny thing is a micro robot which is moving on the petri dish. You're seeing a top view image. Those yellow compartments are actually gel blocks, which can encapsulate cells, and which can be in any shape, right? As I said, with UV lithography, you can create triangles, squares, circles, and with the joystick, we are able to move this tiny permanent magnet or micro robot. It's crawling motion, and we are able to push physically. So it's like a micro factory, right? A man or a robot is just pushing those building blocks, which are cell encapsulating blocks, into any geometry you want. So it's a bit different from bioprinting. So bioprinting is, so I have to obviously highlight the advantages of different technologies. I should be honest, right? So the bioprinting is obviously a more scalable technology. So it is more faster motion, and it's more it's more scalable, especially if you're looking for some scalable tissues like centimeter scale or larger scale of tissues. Bioprinting is a better approach, right, for scalable tissues. In this case, this is a very novel approach, and we were trying to show that we're capable of move these building blocks on demand. And one advantage of this approach compared to the bioprinting, theoretically, in many bioprinting technologies, once you deposit the building block or the gel itself, the relationship between the nozzle or the extrusion tip is broken, right? So you're not able to manipulate whatever deposited onto the the receiving surface. So in this case, in terms of technology, you're always capable of manipulating the locations of these building blocks. Why this can be important? For instance, you can create some complex 3D architecture or 2D architecture, and then you can also park, right? You can put these building blocks as parking of these blocks. So you can park, for instance, a growth hormone encapsulating building block next to this complex 3D architecture, and after certain elapsed time, you can also remove that building block in an automatized way from that area, again by using the same robot, right? So there can be that kind of dynamic relationship between the controller and the resulting structure. So theoretically, there is that kind of advantages. Obviously, this is single robot, but this can be also parallelized with multiple robots. So multiple robots can work in the meantime, again, like a microfactory, and the scalability of this technology can be also increased. I would say it will be still difficult to probably to reach the scalability levels of bioprinters, but still there's a room to improve the scalability of this technology. So we show some other 2D assemblies, like different geometries, like Lego structures with different colors and different shapes. We also showed actually again another distinction or advantage compared to bioprinting. We're not just capable of move these gel blocks, but we can also move actual rigid components like cylinders or spheres. So here, for instance, we show that we're capable of putting small gel blocks, but we also put some rigid spheres, for instance, polystyrene spheres and copper cylinders. So here, we didn't show a working end application, like, for instance, it can be a sensor for electrochemical detection, right? So you may potentially a more advanced version of this technology can potentially create some electrodes, right, on some bendable structures like wound or some soft degradable patches. You may potentially need to create some electrodes as well for, let's say, electrode detection. So there's some that kind of end applications as well. So this is currently far from being addressing that kind of end application, but just to show the proof of concept, we are able to pattern not just soft structures but also some rigid structures like copper or polystyrene structures. In this project, we also show that obviously the viability of these blocks once they're patterned with the micro robot, because it's basically it's a paramagnetic encapsulating resin. So we want to see that if the resin or the paramagnetic particles have any negative effects on the cells, right? So we show some viability data for various time points. We also show by immunochemistry whether the cells are not just live or dead, but they also have the proliferation capacity. So they're able to grow. They have the capacity to grow and multiplex. So we staying with the Ki-67, I believe. We show that this cells have the proliferation capacity. We also show some 3D structures, some Mickey Mouse, Disney images, just to show that we're capable of creating any architecture we want. So yeah, I have few slides just to show that we're also working on bioprinting. My lab is working on bioprinting. We created again a low-cost bioprinting bioprinter setup in-house. So we design everything. So here actually we have this syringe pump images, but we also actually in the article that we published, we show that we use custom-made syringe pumps as well. So we have custom-made control reservoir, which is capable of both droplet-based printing and also extrusion-based printer. So we're showing that we're able to, pattern these droplets, which encapsulate cells, and also some mesh structures, right? So some characterization about the cross-linking mechanism here, and also the spatial resolution. We're ejecting these droplets, but we want to see that it's not affected by some circulating air in the environment, right? Whether the distance between the receiving surface and the ejector tip is optimized well or not, so that the droplets are hitting always within a reasonable structure, within a reasonable standard deviation. So we also show that some printing parameters are affecting the these resolutions in part D, whether we are able to create smooth, filaments. So as you can see, I believe these were droplets. So we are ejecting different droplets, adjusting the distance between the droplets, and here we are showing for different flow rates, right, from a millimeter per second to 7 millimeter per second, the filament base, extrusion base. So that was the previous one was droplet base. This one extrusion base. So we're creating filaments, continuous stream of liquid for various ejection velocity. The resolution that we're creating is different. We also characterize that part. Again, we studied the cell viability in these droplets and filaments. This is filaments, and also in droplets as well. We studied. So just to briefly talk about some end applications. So my TÜBİTAK project, maybe you saw some Twitter ad that I have been looking. We have been looking for students and postdocs for my lab, and the one of the main projects that we're going to working on is Glioma on a chip project. So that is basically a multiplex microfluidic setup, which has dozens of chambers in it. And also within these chambers, we're going to create these bioprinted or photolithography patterned gel blocks, which encapsulates these glioma cells in certain configuration, which I'm not going to go detail. But basically, we are going to create this brain cancer model on a multiplex microfluidic setup, which will help us to analyze the effects of certain molecules, which can be some drug molecules and some other molecules, on the migration patterns, on the behavior of these brain cancer cells in a very multiplex manner. So we're gonna send different concentration of certain molecules into different chambers on the same chip, and at a very high throughput. Our goal is to get rid of or create an alternative model to animal testing, right? Because for some drug testing, you would need to plan these parametric studies on animals, right? For instance, if you need to say that study these 3 drug molecules, you can create how many? So like 6 combinations, right? If the concentrations is same. But if you're also changing the concentration, say from, I don't know, X configuration to 5X configuration, 5X concentration for each molecule, and combination of like A plus B, A plus C, or A plus B plus C, or just A, B, just C, then you have lots of combinations of these analysis. And in that case, you would need to use hundreds of animals, mouse models, to be able to test all those drugs. So this multiplex chip model, where we have dozens or hundreds of chambers, and these small tissue models in each chamber, and with precise control of liquid and molecule to be transported, you're basically doing this entire 100 animal experiment on a single chip. So this is just some preliminary data with the some iPSC-derived cortical progenitor neurons cultured in the JELMA, and which shows that they're viable in our JELMA model. Just to give you some hint about the next steps that we're thinking. So yeah, before coming here, I had also this independent lab, my own lab in the University of Connecticut for a couple of years. So it just shows that we're able to, with the bioprinter setup, we're able to pattern, whatever geometry we want. Here we wrote, UConn, so University of Connecticut, CONN, and some other characterization. But just to wrap up my talk, so bottom-up tissue engineering can address the challenges of tissue engineering. So here the goal is by using some novel approaches like microrobotics or more established technologies like bioprinting. Our goal is to achieving complex three-dimensional cellular architecture and organization and control over cellular proximity. So we want the distance, the cell density in any XY location as we want on demand. And this is also important to enhance the transport through scaffold porosity, which would mimic the network in vivo in our real tissues. So some other points. Obviously, microassembly of gels can offer precision, yet limited scalability, as I mentioned before. On the other hand, it can find applications in some microphysiological applications, like this organ on a chip or tissue on a chip models, with potential room in the fabrication aspect as well, like using multiple robots. And the third point is the bioprinting offers scalable constructs, and our lab has the technology and expertise on that domain as well. So yeah, these are some of my previous funders when I was at UConn. So I was funded through this American Heart Association. Some of this work was accomplished by them with the fund by them. We obtained also fund from NIH later, and also University of Connecticut. Some of our collaborators on point of care research, like Ionita, Matthew, Farzana from Yale. So yeah, I would like to thank everyone. Teşekkürler ve dediğim gibi şu anda öğrenci arayışındayız. Yani ilgili olan öğrenciler lütfen e-mail atmaktan çekinmesinler. Ve de şu şekilde bir de şu şekilde şunu da hocam söyleyeyim, yani bu çok interdisipliner çalışıyoruz. Öğrenciler hani şey olmasınlar, ya benim işte biyokemistri background'um var, ben robotikten ya da elektronikten anlamıyorum. Bizim zaten aradığımız yani özellikle lisans ya da işte doktoraya başvuran öğrencilerde yani dokun mühendisliğinden çok iyi anlayabilirler, biyokemistriden anlayabilirler, cell culture'da tecrübeleri olabilir. Ama diğer alanlarda da kendilerini geliştirmek istiyor olabilirler. Biz bunlara açığız, ya da elektronik biliyorlardır, iş bilmiyorlardır. Biz bu environment'ı yaratıyoruz. Yani kendilerini o alanlarda da geliştirirken bize de katkıda sunabiliyorlar. Çok konuştum. Teşekkür ederim.
Evet, hocam. Ben çocuklara zaten söylüyorum sürekli hocam derslerde de. Ben mesela kendim işte biyomedikal mühendisiyim lisanstan. Biyomühendislik yüksek lisans yaptım. Benim doktoram mekatronik. Efendim doktora sonrası işte MIT'de medical engineering falan, orada da çalıştık. Medical engineering, yani ne o Harvard Medical School'da, tıp fakültesinde bile çalışmış bulunduk. Yani hepsi artık birbirine girmiş. Siz de bildiğim kadarıyla makine mühendisiniz değil mi?
Aynen.
Evet.
Yani
benim doktor hocam da makine mühendisiydi yani. Ahmet hocam da fizik hocasıydı. Yani sürekli bu alanlar birbirine girmiş durumda. Öğrenciler, ben
evet,
sürekli söylüyorum yani, ufkunuzu siz sadece sınırlandırmayın. Her şeyi yapabilirsiniz.
aynen. Bir de çekinmesinler yani. Ya ben işte hani şu labda biraz çalıştım, ben bu konuya hakimim. ya bir sene, 2 sene ya da master'da şunu öğrendim diye düşünmesinler. Ben yani hem teorik çok çalıştım. Yani sonra deneysele geçtim. Deneyselde çok çalıştım. Yani konularım çok değişti. Önemli olan yani o kişisel cesaretinizin olması ve doğru ortamda bulunmanız. Ve de o sizin CV'nizin yani diğer bir sonraki aşamalarda pool'dan, o havuzdan ayrılmanız konusunda çok yardımcı oluyor. Yani siz ileride şimdi doktoranızı yaptınız diyelim işte Ali Hoca ile ya da benimle. Daha sonra da başvurduğunuzda postdoc şirketlere bile yani farklı tecrübeleriniz olması gerçekten çok kritik.
Evet. Hocam akademik olarak bu çalıştığınız mikro robotikler ne kadar mikro? Yani
Bunlar 750 mikron falan. 750 mikronlu bizim şeyde kullandığımız. Bizim gel blokları ise kalınlığı mesela 150, 200, 250 mikron. Fakat o yani yukarıdan gördüğümüz karelerin büyüklüğü ise mesela 500 mikrona 500 mikron. Yani kalınlık yani width ve height 500 mikron olabiliyor. 1 milimetre olabiliyor. Şimdi aslında bir tane
malzemesi nedir hocam? Yani çok rahat kontrol ediyordunuz da.
bu rezin ve rezinin içerisinde de süper paramanyetik partiküller var. Yani
Nasıl kontrol ediyorsunuz o kadar rahat?
Ya bu işte zaten elektromanyetik coil'larla sen manyetik alanın öyle bir yaratılıyor ki bu şeyde rotating bir hareket yaratıyor. Yani bu bizim gördüğümüz oradaki ufak mıknatıs yani rectangular prism e, e, temas ettiği noktayla manyetik field'ın etkisiyle o sticky point her zaman değişiyor. Yani bir sliding şey var, hareketi var.
Hall effect dedikleri miydi? Hall effect diye bir şey vardı, o muydu? Öyle bir şey miydi? Yanlış hatırlıyor olabilirim.
Yani, Hall effect değil tam olarak. Sliding motion'ın adapte olması. Yüzeydeki roughness da çok önemli. Yani onunla da ilgili aslında slide vardı da ben onu eklemedim. Ama yani bu konularda yani bizim yani biz bunu Nature Communications'a yayınlamıştık Metin Hoca'yla. Fakat bu sliding motion çok detaylı bir şekilde Metin Sitti hocamızın yani çok sırf o olaya odaklı makaleleri de var. Dolayısıyla bizim makalede teori kısmı biraz daha limited. Buradan hani öğrenciler de bakmak isterlerse direkt Metin Hoca'nın sayfasından da girebilirler ya da bana mail yazabilirler, ben yönlendirebilirim.
Bu hocam şeyde mesela push ediyorduk yani sürekli o mikro robot bir push etkisi vardı ama mesela bir kavrama hareketi yapma şansı var mı? Ya da böyle robotlar var mı? Sanki öyle birkaç yayına denk gelmiş
Var.
ama.
Ya ben şeyde literature'da mesela bir tane Hava ile bir grup var. Mesela ya Metin Hoca'nın da tabii çalışmaları var onda. Gripper şeklinde de davrananlar var. Yani objeyle mesela kenetleniyor ve o kenetlendiği objenin manyetik olması da gerekiyor. Zaten robotun kendisi manyetik bir responsive. Kenetlendiği gripper'ı hareket ettiriyor manyetik field strength'le ve 3D hareket yaptıran çalışmalar da var. Yani sadece 2D hani yüzeyle temas halinde de kalması gerekiyor. Literature'da öyle çalışmalar da var.
Yani siz mikro robotu şey için kullanmışsınız yani bir bioprinting metodu gibi kullanmışsınız anladığım kadarıyla ama
evet.
Bunu şey olarak da hakikaten mikro robot gibi gelip de mesela vücuda alacağız işte ileride. İnsan
Evet,
vücudunu tutacak, çekecek yani bir hastalığı falan.
Yani benim kişisel olarak ilgim yok o alanda. Ama yani onda da ciddi challenge'lar var. O konuda da çalışanlar var. Yani hani robotu vücudun içerisinde yani mesela işte kanserli dokuya ya da işte hücrelere işte mesela drug taşımak için. Yani bu tarz çalışmalar da var. Yani bazı onlarla ilgili çalışmalar var. Şimdi ben onları yorumda bulunmayayım. Yani o konuda çalışmıyorum. Aklımda da hani söyleyebilirim ama kendi alanım değil. Ama yani çok kolay değil. Yani robotun vücut içerisinde kontrol ettirilip hücreleri bulması ve hücreleri yeterli ölçüde etki yapabilmesi ve şeyin de Sonra da robotun bir şekilde vücuttan atılması ya da elimine edilmesi kompleks bir problem. Bazı başka yöntemler de var. Yani onun yerine kişinin kendi hücrelerinin repurpose edilmesi. Yani bunlar personalized medicine'a falan giriyor. Benim o konularda çok şeyim yok. Çalışmam yok. Yani sadece reviewer olarak yaptığım şeylerden biliyorum. Yani kendilerine ait challenge'ları var. Ama benim buradaki konseptim yani biomanufacturing ve point of care diagnosis.
Tamam hocam. Harika. Çok sağ olun. Evet arkadaşlar, o Barış hocam da gelmiş de, Barış Binay hocamız var, bizim bölüm başkanımız. Burada mı bilmiyorum da şu an cevap verebilecek durumda mı?
Buradayım Ali, dinliyorum.
Evet hocam. Hoş geldiniz hocam.
Hoş bulduk.
Ben
Savaş Hoca'ya hoş geldin diyorum.
Ben sizleri göremiyorum da şöyle şunu yapsam aslında. Yani şu anda görüyorum ama siz de kendinizi görüyorsunuz. Yani.
Yok. Ben varım zaten bir tek hocam. Diğerleri yok. Bir de şimdi Numan hocam çıktı da. Numan hocam merhabalar. Ama istemeden çıktınız herhalde.
Merhaba, herkese çok selamlar.
Merhabalar hocam.
Teşekkür ederiz. Ben birazcık tabii geç katıldım. Başını kaçırdım, kusura bakmayın. Ama katıldığım kısmıyla da istifade ettim. Çok teşekkür ederim. Bizim arkadaşlara da bu organizasyon için çok teşekkür ederim. Aslında Ali Hocam bana söz hakkı vermişken belki bir soru sormak isterim Savaş Hocam'a. Savaş Hocam, şimdi tabii bir kısmınızı kaçırdığım için konuşmanızın çok net bilmiyorum. Siz mikro akışkan kanalları hangi yöntemle üretiyorsunuz? Hepsini bioprinting mi yoksa PDMS cam şeklinde normal geleneksel litografiyle ürettiğiniz veya kullandığınız mikro akışkan yapılar var mı? Varsa Koç'ta bunları kendiniz üretiyor musunuz? Onu da sormak istedim.
Hocam şöyle biz yani bayağı bir farklı yöntemle çalıştık. Yani PDMS'te de çalıştık. Benim kendi labımdan mesela bu işini kaçırdıysanız maglev teknolojisinden bahsettim. Mesela bu manyetik levitation'la partikülleri ayrıştırmakta. Mesela onda bir projede şöyle bir şey yaptık. O manyetik separator'ın içerisine konulan kepilerin ucuna mesela PDMS çip geliştirdik. Bu mesela partikülleri sadece ayrıştırmıyor. Bir de downstream'de farklı rezervuarların içerisine yollayabilmek için. Dolayısıyla yani sorunuzun cevabı PDMS çiplerle çalıştım. Onun dışında mesela şeylerle de çok çalıştık hocam. Bu akrilik sheetleri mesela purpose etmek. Akrilik sheet'i mesela laser cutter'la kesip double sided adhesive layer'la onun da şöyle bir avantajı var.
PMA tarzı bir malzeme mi?
Ya o bildiğiniz hocam akrilik sheet. Akrile Türkçesi de akrile herhalde.
Akrilik,
yani onu lazer cutter'la all through kesebiliyorsunuz Bu şu açıdan iyi. Yani özellikle point of care'ı gene öneriyorsanız ben böyle ya bunlardan çok sayıda üreteceğim. Resource Limited Sharing'de mesela benim eski danışman hocamın öyle yine HIV çalışmaları vardı yine Afrika'da vesairede ona uygun bir şekilde. Onlarda mesela yine yani problemi nasıl çözerizden akrilik sheet'e gelindi yani kendisinin çözümüyle. Ucuz bir şekilde o çipleri nasıl üretiriz? Onda da tabii problem oluyor. Yani çip çok kompleks olmuyor. Ama ucuz olabiliyor. Onlarla da çalıştım. Onun dışında ben kendi labımda çipleri 3D printer'la da ürettim. 3D printer'la onda da tabii resolution limitleri var. Fakat onlarla da çip ürettik ve hatta çipin içerisinde dokuları da tuttuk ve doku hücreler viable kaldılar. Hatta onu Ali Kalem Hüseyin'i ile yayınladık. Biofabrication dergisinde yayınladık. Onu burada koymadık. O da mesela proof of concept çalışmaydı. Yani ilk kez bir 3D printed çipin içerisinde patentlenmiş hücre içeren dokuları gösterdik. Yani görece basit bir makaleydi ama proof of concept ilk kez biz gösterdik yani 3D printed çipin içerisinde. Şöyle hocam, Koç'taki var olan altyapıyla ilgili de cevaplayayım. Onunla da ilgili bir şey söyleyeyim. Yani siz mi yapıyorsunuz? Şimdi benim 12 ay falan oldu hocam geleli. Tabii biraz şu anda lab'ı tam böyle ramp up döneminde. Ama Koç Üniversitesi'nde biz şimdi çok güzel bir clean room facility kuruldu. Yepyeni. Önceden başka bir clean room vardı. O hala duruyor. Ama bir tane daha büyük bir clean room facility kuruldu. Dolayısıyla bu Gliomo projesinde, çünkü o çok multiplex bir çip. Onun tasarımını göstermedim bu sunumda. O karmaşık bir çip. Bir sürü şeyler var. Rezervuarlar var ve birbirlerinin bağlantılı olduğu yerler var. Yani konsantrasyonların adapte olması, mikserleri falan var. Onda mesela kullanacağız tabii. Yani soft litografi ile yapacağız. Clean room. Ama mesela point of care araştırmalarında yine 3D printed çipler kullanacağız. Yani daha hızlı bir şekilde prototyping yapabilmek için.
Ali Hocam, vaktiniz varsa çok kısa bir şey söyleyebilir miyim?
Tabii buyurun hocam, buyurun demek.
Ben aslında bu soruyu şunun için sordum. Gebze Teknik Üniversitesi'nde bizde hem temiz oda da var hem de benim kendi mikro akışkan çip laboratuvarım var. Ben fizikçiyim, fizik bölümünde öğretim üyesiyim.
Hocam daha dün herkese soruyordum bizde temiz oda ultraviyole var mı diye. Barış hocam da şahittir. Kimse de dönmedi. Numan hocanın var demedi. İyi oldu.
Ofis telefonunuzdan, lab telefonunuzdan aradım Ali Hocam bu hafta aslında.
Hadi ya.
Tam denk geldi o zaman, iyi oldu. Şimdi Savaş Hocam, bizdeki temiz odada maske yazma imkanı var. 1 mikrona kadar maske yazabiliyoruz. Bu zamana kadar hem kendi işlerimizde kullandık hem de dışarıya, Aselsan'a, İTÜ'ye, Bilkent'e birçok yere de hizmet verdik bunun için. 1 mikrona kadar krom maskeler, soda lime veya quartz maske hazırlıyoruz. Bunun haricinde bizim mikro akışkan çip laboratuvarında spin kaplamasından UV litografi işlemine, sonra çip paketlemeye kadar PDMS mikro akışkan çipler veyahut da cam PDMS mikro akışkan çipler 2 sene önce Aselsan'a botoks ve şarbon deteksiyonu için Boston'da yapılan bir çipin bir benzerini Türkiye'de üretilebilir mi diye yapmıştık. 50 mikron yüksekliği olan antikor falan ekilebilen bir çip dizaynıydı. Şu anda da Boğaziçi'nde biyomedikal mühendisliğinde belki tanırsınız Özgür Kocatürk Hoca var.
Ben tanıyorum mesela.
Evet. Onunla ortak bir iş yapıyoruz. Sinir ve kanser hücrelerinin birbiriyle etkileşimini incelediğimiz bir çip. İkisi farklı kanalda ekiliyor ve büyütülüyor hücreler. Arada başka şeyler var, tüneller var. Yüksekliği 5 mikron, genişliği de 7 mikron civarında. Yani hücreler geçemiyorlar ancak aksonlarını uzatıp haberleşebiliyorlar. O çipi de biz burada üretiyoruz. Bizim laboratuvarımızda üretiyoruz. Ama hücre deneyleri Boğaziçi'ndeki hücre laboratuvarında yapılıyor. Dolayısıyla
kiminle hocam çalışıyorsunuz Boğaziçi'nde?
Özgür Kocatürk, biyomedikal mühendisliği.
Benim hocam bu 22-32 yani yarı yarı paylaşıldı. Ben Boğaziçi Biyomedikal Enstitüsü'nde de şimdi Bora Hoca'yla birkaç hocayla çalışıyorum. Yani oradan da orada da şeyimiz var. Ama ben sizin bahsettikleriniz hocam çok ilgimi çekiyor. Özellikle yani bu maske üretiminde sizinle kesinlikle kolaborasyon yapabiliriz. Ben o konulara da çok açığım zaten. Dolayısıyla temas halinde kalalım. Diğer bahsettiğiniz projeye de tabii bir destek herhangi bir seviyede verebilirsem mutlu olurum yani.
Şu ekranda görüyor musunuz şu an?
Görüyorum, evet.
Bu ekranda burası hücrelerin ekildiği kanal, sağ tarafta başka bir kanal daha var. Burası da hücrelerin geçemeyeceği kadar küçük tüneller, 5 mikron yüksekliğinde, 7 mikron falan genişliğinde. Bunu Boğaziçi ile ortak çalışıyoruz. Çipi biz burada öğrettik. Öğrenci geldi burada, ona da öğrettik. Kendisi yaptı. Şimdi hücre ekimini yapıyor. Şu bahsettiğim de, çok affedersiniz, hemen göstermeye çalışayım. Şu da Aselsan'a ürettiğimiz bu Boston'ın dizaynı, özgün bir dizayn değil. 50 mikron yüksekliği bu kanalın. Burada antikorlar ekilmiş vaziyette. İşte bahsettiğim gibi botoks ve şarbon deteksiyonu için PDMS cam tabanlı bu. Diğeri de PDMS cam tabanlıydı. Yani 5 mikrona kadar istediğimiz herhangi bir şeyi yapabiliyoruz. Onu sizinle de paylaşayım dedim. Bilginiz olsun.
Tamamdır.
Numan
Hocam biz
bizim
ayrıca bir toplantı yapalım. Ben yani hocam mutlu olurum. Yani siz vaktiniz olduğu bir zaman bana hocam e-mail atarsanız biz ayrıca bir hani şey yapabiliriz.
Olur.
Orada da yani Aleyna'ya da bir sormak istiyorum da öğrenciler, yabancı öğrenci var mı? Yani ben öğrencilerden de soru varsa hocam onları da bir
Tabii,
İngilizce
tabii.
cevaplayayım. Biz ayrıca bir proje toplantısı, ben istediğiniz zaman olurum.
Numan
Müsait
hocam,
olurum.
bizim de bir şey var. Çip üstü deri projemiz var da. Yani parası falan aşağı yukarı hazır gibi. Sizle de irtibata geçelim. Ben fellik arıyordum. Ultra böyle
Tamam.
işte fotoğrafı nerede yapabiliriz falan diye. Zaten varmış, üniversitede varmış. Bana diyorlar ki Bilkent'e gidin. Unama gidin.
Bu
Diyorum Ankara'ya niye gideyim ben korona zamanında?
hafta aradım daha. Şimdi Savaş hocamın sunumunu çok sabote etmeyeyim ben.
Evet.
Diğer arkadaşlar sorsunlar. Çok teşekkür ederim. Tekrardan vakit ayırdığınız için harika bir sunumdu. Sağ olun.
Ben teşekkür ederim. Temas halinde kalalım hocam.
Tamamdır.
İşte akademisyenler arasında böyle kopukluk oluyor hocam. Her zaman yapamıyoruz. Koordine olamıyoruz yani. Çok koordine olsak güzel işler yapıyoruz da olamıyoruz maalesef. Evet, Aleyna arkadaşlar yapmayın, çekinmeyin. Yani hocamız, Savaş hocamız dünya gezmiş, görmüş. Yapabilirsiniz. İstediğiniz gibi soru sorun. Kariyerle alakalı da olabilir. İlla bilimsel olacak diye bir şey yok. Bilimsel de sorabilirsiniz tabii de. Yani kariyerle şimdi hepimiz biyomür mücadele ediyoruz. Bunlara yönelik mesela merak ettiğiniz şeyler varsa mutlaka sorun. İngilizce bilmiyorum, Feyruz falan var ama Feyruz Türkçe anlıyor zaten. İngilizceye çevirmiyorum. İngilizce de sorabilirsiniz elbette ki. Evet.
Hocam sanırım kimsenin sorusu yok.
Ya niye sorusu yok? Vallahi billahi. Hocam stajyer falan alıyor musunuz Kut'tan? Onlar sormadan ben sorayım bari. Staj büyük mesele yani. Lisans olunca en büyük sorun bu. Staj yani.
Stajyer de alıyoruz, doktor öğrencisi de alıyoruz, master da alıyoruz. Aleyna sen yani
Hocam.
bu yani Twitter'da da var. Ben o sana e-mail adresim de var. Yani eğer hani başka bir ortam olur da öğrencilere bir sunum yaptığın zaman fırsat olursa bir konuşma esnasında da bahsedersen sevinirim. Belki biraz İngilizce olduğu için de çocukları turn off etmiş olabilirim. Ama yani gerçekten Türkçe sunumu çok yani hem durarak konuşuyorum. Yavaş olacaktı. Biraz ondan dolayı bu şekilde yaptık.
Yok hocam yok, hiç önemli değil. Zaten biz okulda da eğitimi %100 İngilizce alıyoruz. Yani katılımcılarımızın hepsi İngilizce biliyor. O yüzden o yönden bir sıkıntı yaşamadık. Sadece belki hafta içi olmasından dolayı olabilir. Yani bilemiyorum katılımdan nedenini. Ama çok keyifli bir sunumdu. Sanırım kimsenin de sorusu yok diye düşünüyorum. Ben az önce mailinizi not aldım zaten. Size dönüş yapacağım. Seminerden sonra. Arkadaşlar sorusu olan var mı? Tekrar ben bir sorayım. Sanırım yok. Büyük ihtimalle size birazdan bir sürü mail yağar zaten. Stajlar hakkında falan. Ben de bir mail sizinle görüşmek çok isterim. Hocam
ben
çok
teşekkür ediyorum o zaman. Ben sana da çok teşekkür ediyorum bunu organize ettiğin için. Hem hocaları hem de öğrencileri bir araya getirdiğin için. Yaptığın iş çok değerli. Teşekkürler.
Ben teşekkür ederim hocam. Çok sağ olun.
Görüşmek dileğiyle. Ali hocam çok memnun oldum tanıştığımızda.
Çok teşekkür ederim. Mutlaka irtibatta kalalım. Proje falan yapalım ya, çıkartalım işte. Postdoc yoksa ben gelirim, postdoc beni alın.
Sonra pişman olmayın.
Yok olmam, niye oluyor?
Tamam, hadi görüşmek üzere. Kalın sağlıcakla. Memnun oldum Numan hocam. Görüşmek üzere.
Ben de memnun oldum. Kendinize iyi bakın.
Arkadaşlar görüşürüz. Kendinize iyi bakın. Numan hocam görüşürüz.